Hello? Yeah. Yes. So thank you to the organizers for inviting me. So I had the privilege of meeting Frank in 1997. There were flood and snow in Spain, in Valladolid, and he gave these lectures on the singularities of two-dimensional foliations and groups. And I read those notes a lot throughout the years. So thank you very much. So throughout the years, I've had the privilege of enjoying his patient listening. And it's a strange privilege because it's shared by many of us. So it's a social privilege. So muchas gracias, Frank, y felicidades. Okay, so I would like to talk about some deformations of some complex manifolds, some compact complex manifolds, non-algebraic ones. And these deformations will arrive through projective structures on curves. Okay, so let me start by telling, so I will take some time before I can state some results, but I hope you oh, that's me. Okay. So let me start talking about projective structures on curves. Okay, so everything will be complex. So if you have a complex curve, you already have your complex structure. So on top of this complex structure, when you fix this complex structure, a projective structure will be an atlas for its projective structure, taking values in P1, such that the changes of coordinates are given by Möbius transformations. So this will be a projective structure. Okay, so this is one-dimensional projective geometry. These are general complex numbers. And some particular cases, particular instances of projective structures can arise through the uniformization theorem. So when you have a complex curve by the Poincaré-Koebe uniformization theorem, you can realize it as a quotient of some group of Möbius transformations, but actually some group in PSL 2R. So these transformations form the group PSL 2C, and it has a subgroup PSL 2R, and then this group will act on the upper half plane and produce in the quotient your manifold with your structure. And so this group will act by Möbius transformations with real coefficients. It's a particular case of the other one, so it will act by preserving this projective structure on the upper half plane, and you will inherit a projective structure in your quotient. Okay, so these are some examples of projective structures that arise in complex curves. Okay, and if you fix your projective structure on your curve, you will have that all the projective structures on it are parameterized by quadratic differentials. So let me write this down. The difference of two projective structures on a curve is a quadratic differential, holomorphic quadratic differential. So let me tell you how this works. So imagine you have, again, a complex curve, and you have in it two different, on the same complex structure, you have two different projective structures. Suppose that we have two charts with overlapping domains. This one is for the first projective structure. This one is for a second projective structure. So this takes values in P1. This also takes values in P1. So this map here, since I'm supposing that they are not necessarily the same projective structures, this map need not be a Möbius transformation. Okay, so it's just a holomorphic map between the intersection of the domains. And to this map, let me call this map F, we can associate the following object in the domain of F. It is given by the Schwarzian derivative. So Z is a coordinate here. And it turns out that this expression defines a quadratic differential in this chart. So you can have a quadratic differential. And this locally defined quadratic differential, by the properties of the Schwarzian derivative, this expression, define a globally defined quadratic differential on this manifold. Okay, so if you have this, so this expression will vanish if and only if F is a Möbius transformation. So if you have Möbius transformation, you will get the zero quadratic differential if these two structures, projective structures, are the same. But if they are different, you will get some holomorphic quadratic differential. And it also works in the other way. If you have a projective structure, you can add a quadratic differential to it, and you will get a new projective structure. Okay, so the difference of two projective structures on a curve is a holomorphic quadratic differential, and from a projective structure, you can add a quadratic differential and get a new projective structure. Essentially, you will have to solve this differential equation, this Schwarzian differential equation, if you have your quadratic differential. Okay, so that's this one thing. And let me tell you about, I will talk about deformation. So as I said, I was going to talk about deformations of manifolds. So, when you have manifolds, complex manifolds, compact complex manifolds are difficult to construct in the non-algebraic case. So algebraic ones, you give formulas or constructions, but there are not that many constructions for non-algebraic compact complex manifolds, on the one hand. So on the other, compact complex manifolds come in families. So it's not always evident, even if you know how to build, how to describe, how to construct a given compact complex manifold, it is not easy to describe the deformations, or it is not given. When you are given your manifold, you are not given a way to describe these deformations. So I would like to describe this. That's the aim of the talk. And to give you a flavor of what's going to come, let me tell you about the deformation of compact curves. Okay, so I said this was an example of projective structure, a projective structure in a manifold, when I have this group, this Fuchsian group, acting on the upper half plane. But in fact, this Fuchsian group will act also on the lower half plane, and you will have a map between these two components of the quotient, essentially induced by complex conjugation. And let me tell you what happens when you deform this group. Okay, so this group sits inside, it's a Fuchsian group. It sits inside PSL2R, which sits inside PSL2C. And when you deform your group inside PSL2C, when you take your character variety in the neighborhood of this given group, you will find that your real line, becomes a quasi-disk, quasi-circle. It's a fractal curve that still bounds two domains, what remains of the upper one and what remains of the lower one. So in each side, you have again, a curve, a compact curve. So in your, when you look at the dimension of this space, of your character variety, mod conjugation, the dimension of this space is 6G minus 6. On one hand, the dimension of your Teichmüller space is 3G minus 3. And the dimension of the space of quadratic differentials this is the square of the tangent bundle of your curve is also 3G minus 3. Okay? Yes. Complex, yes, everything is complex.
The first one should be PSL to C.
Yes, indeed. Indeed, thank you. Complex, everything is complex. Okay, so, and what's happening here is what's understood by Beers through his simultaneous uniformization theorem. And he says that, he says that this group contains two copies of Teichmüller space. It is this Cartesian product, fits inside here. And the way that he constructs this is through projective structures and quadratic differentials. So let me tell you what I am understating Beer's results, but what happens is the following. So my group can be deformed with 6G minus 6 parameters. Okay? So what I can do with this deformation is, and each time I get a new quotient here, the new group will act on this domain in P1. So this is still a domain. These are two domains in P1. And it will act through Möbius transformations with complex coefficients. So it will act by preserving a projective structure. So in the quotient, you get each component of the quotient inherits a projective structure. So what happens is that if I deform my group by fixing the complex structure on one factor, say the upper one, so I will deform my group preserving the complex structure there. I will deform my projective structure. Okay? And what Beers says is that by deforming this projective structure, you will realize locally all the deformations of your second. Okay, so the Teichmüller space, see if this is S, so if this is S, and this is, say, S bar, you have that the Teichmüller space of S bar injects into the space of quadratic differentials of S, local quadratic differentials of S. Okay, so this is quadratic differentials, holomorphic quadratic differentials on S. And these are the complex structures on S bar. Okay, so you have a couple of manifolds, compact complex manifolds. By fixing the complex structure in one and deforming the geometry, you will realize the formations of the complex structure in the second one. Okay.
Isn't the quadratic differentials parameterizing all projective structures on the same surface?
Yes, the same curve, yes. So if I have a map between, say that again, George.
If I just do this change of constructing a new projective structure from a given one using a quadratic differential,
yes,
wouldn't I end up in the same Riemann surface?
Yes.
And what you're saying here?
So so I have two copies. So I fix, so here I have, the quotient has two connected components. What I'm saying is, if I deform, and these come by pairs. So I'm saying is, if I deform if I fix the structure, the complex structure on one, but I deform the projective structure, this one, I will see the new projective structure, and we'll have a complementary, some other side, there's a new curve accompanying this deformation of the projective structure. And when I look at what all these curves on the other side, when I look at them, they deform the projective structure. So the Teichmüller space of this quotient of this lower half plane embeds into the space of quadratic differentials of your first curve. Okay.
Upstairs, nothing changed?
Upstairs, the geometry changes, but the complex structure remains, and downstairs, everything changes. So everything changes. Okay, and this is a consequence of, it's an understatement of Baer's simultaneous uniformization. Okay, so we will be playing this game in a foliated setting. So is this clear? Is this any questions here? So, okay, so let me tell you what the game will be. So I will tell you more about this setting. So let me consider in C3 Hermitian form with signature 2-1. And then consider the group U21 sitting inside GL3, preserving this form. Okay, so this form defines a space in C3 of negative vectors, and when you projectivize, you end up in P2. Inside P2, you will get a round ball coming from the negative vectors, which is, and it inherits a geometry, which is the two-dimensional complex hyperbolic space. So this group now, the group acting in the projectivization is this PU21, this Lie group, this real Lie group, PU21, and it acts linearly on P2. It preserves the ball, and inside the ball, it acts by preserving a Hermitian metric, positive definite Hermitian metric with negative curvature. Okay, so this is on C3, I have this. And I want to consider some quotients by this group. Okay, so now I'm coming closer to my setting, and the setting is that of flag manifolds. Flag manifolds, two-dimensional. Okay, so a flag in projective space, we have seen this before, is P2, and a flag will be a point, a couple of a point, and a line, which are incident to one another. This is a three-dimensional space. You have a two-dimensional space of points, a two-dimensional space of lines. There's one dimension, plus one condition for the incidence relation between them. Your full group, PGL3, acts transitively on the space of flags. And moreover, this space of flags has two tautological foliations, which are given as follows. So the flags are a couple of points. And you can consider the foliation whose leaves are the couples point line that share the same line. Okay, so this is a foliation. So I will move the point within the line. The leaves are, you have the relation P1, L1 related to P2, L2, and the leaves of F are the couples having the same line, okay? So you have another one, a dual one, when you fix a point and you make the line move, okay? But I will be interested in this one that I will call F. And notice that it has a projective, every leaf of this foliation has a natural projective structure because it is a projective line, okay? So the leaves are parameterized by, so it's just, you fix the line and you move the point. This line, but it's a line, it's a projective line, and it has a projective geometry, a natural one, okay? And if I act by the whole group of linear transformations of P2, I will act on my flag manifold because I will transform points in points, lines in lines. I will preserve my incidence relation. I will preserve my foliation. And everything will be invariant by these groups, okay? Okay. And I will be interested in the quotient of some domains by some lattices in this group PU21. So with respect to the group PU21, there are three invariant domains in the variety of flags. And these three invariant domains are as follows. I will give this schematic presentation. So this is my first domain. Okay, so I will draw here my hyperbolic ball. And this first domain is given by the flags, point, line, incident pairs of point and line, where the point is inside the ball, inside the hyperbolic ball. Okay? There is a second domain, so I will call this one X. There is a second domain where my point is outside of the ball, but my line intersects the ball transversely. I will call this one omega. And there is a third one where the point is outside, the line is completely outside of the ball. Okay? I will call this one Y, but I won't really be looking at this one. I will mostly be looking at these other two. Okay? So these are two open sets. They are invariant under the action of PU21 because it preserves the ball and its interior. And it is also a subgroup of the linear group. Okay? Now, so these are open domains, X and omega. They sit inside this flag manifold. And they have this, I have this foliation here in all the space of flags. And when I restrict to these two, to either one of these two open subsets, well, they remain foliations, and they still have projective structures. But now the projective structures have changed, because here, each time so my line, which was a global P1, it intersects the interior of my ball along a disk, a round disk. Okay? So what I have here is I have a foliation, let me call it Fx, and I have here a foliation by lines, by curves, non-singular foliations, F omega. And its leaves are disks, but not just from the conformal point of view, but from the projective structure point of view. These are round disks. These identify to the intersection of this line with a ball, with a round ball, so these are really round disks. Okay? So I have projective structures, and these projective structures vary holomorphically when I go from leaf to leaf. So this is what we have called foliated projective structures, just projective structure. You have a three-dimensional manifold, a one-dimensional non-singular foliation. On each leaf of the foliation, we have a projective structure, and these projective structures change holomorphically from leaf to leaf. Okay? So that's the setting. And now, as I did before, I can consider the So I will leave that drawing so you know what x and omega are. And now I can consider gamma a co-compact lattice. And I can take this quotient x, and I can quotient it by gamma, and I can take my omega and quotient it by gamma. Okay? So since I took a compact lattice, and in fact, my group PU21 acts both on x and on omega with compact stabilizers, my quotients will be compact manifolds. Okay, so these two are compact manifolds. They will be foliated, so I still have a foliation. Let me call it still fx, even though I took the quotient by gamma. So I have here f omega, a foliation. This one is algebraic. In fact, when I take the interior of the ball and I take the quotient under the action of my group, it will be a complex hyperbolic two-dimensional manifold. And what I'm taking here by taking all the directions, all the lines that pass through a given point, which is what I'm adding, is passing through the compactification of the to the projectivization of its tangent bundle. Okay, so it's something that's produced from an algebraic manifold. So these are three-dimensional manifolds. This one is algebraic, but this one is not even Keller. And this is a result by Toledo and Mueller. And in fact, this manifold has gathered the attention of a lot of people. Griffiths, Schmidt, Langlands, Williams, Carayol, because they are interested in their cohomological properties in some vanishing theorems related to some homogeneous line bundles, the cohomology of some homogeneous line bundles that appear in them, and that will be related to what I want to discuss. Okay, so these are very different, but at the same time, they are very much alike. So let me draw this here. Okay, so there's a strong relation between these two that I will draw here. So where is the
So the one in the left is uniruled, the other not, right?
This one is uniruled, but with respect to the other foliation.
Yeah.
So the foliation that I did not tell you about, which I am not writing, this is uniruled. So it is the projectivization of the tangent bundle of the complex hyperbolic manifold, algebraic, uniruled, but this foliation is a foliation by disks, and it has a very complicated dynamics. It's essentially, so these lines, we have here, inside the ball we have hyperbolic geometry, and these lines are totally geodesic with respect to this complex hyperbolic geometry, so it is essentially a geodesic flow kind of dynamics. So it's a very, very complicated foliation. And in fact, these two are very much alike. So
that was not the question. The question was if the one on the right is uniruled or not.
no, it is not. No.
Thank you.
Okay, so let me do, again, the drawing that's on the left. So I have my ball here, and I have a point. This is the x side, and I'm in x. And there is a natural way to associate, there's a natural way to identify these two spaces. So here, what I have is a point and a line, a point inside the ball and a line. And here is, what I have is a point, a line that intersects the sphere and a point outside. So if I take a point here, PL in X, I can associate a point. So you see, so here I'm considering a flag in the space of flags of P2. This is my complex hyperbolic space. And the intersection of my ball with this line is, so that's a line, and here's a point P, is a disk. So I can consider the inversion along this line with respect to this disk. This is canonically defined, and it defines a point outside the disk. And all this is equivariant with respect to all the groups that have appeared here. It's equivariant with respect to the group PU to 1, which preserves the ball and acts linearly. So there is a canonical way to produce from a point in X, or even in the quotient, a point here. So these two are real analytically diffeomorphic. Okay. So this real analytic correspondence will map one manifold to the other. It will reverse the orientation along the leaves of my foliation. But transversely, as transversely holomorphic foliations, they are the same. I did not change that. So the transverse geometry of these two foliations is the geometry of the action of my group on the complex ball, and that I have not changed. So what I have changed, so these are different. These are different from the complex point of view, but from the real analytic one, they are the same. Okay, just change of orientation. But you know, these are very different manifolds. Okay. So that's that. So the leaves here, I have my leaf L of my foliation. It's a disk. And I told you before that when I have on a curve a quadratic differential, I can add it to a given projective structure to produce a new one. And that's what we're going to do here with all these leaves that are in my foliation X. So for it, I will do a foliated version of what I did before. So I would look at quadratic differentials on this manifold along the leaves. Okay, so these live here. These are quadratic differentials along the leaves of the foliation. And these are algebraic Keller manifolds. So as soon as your first Betti number here is non-zero, you will have holomorphic differentials, and then you can take the square, and then you can produce quadratic differentials along the leaves. So, and then it's easy to construct. There exist lattices that behave like this. So there exist situations when I have many of these, or this space is non-zero. So this is a vector space, a space of sections. What happens is that I can take one of these quadratic differentials along the leaf that's close to 0, that's small with respect to the Poincaré metric on each leaf, which varies continuously, this Poincaré metric. So if I take a sufficiently small quadratic differential, I can add it to the projective structures on the leaves of Fx. What this will do is, this will, by a theorem of Alfors, if this is small enough, I will start with in a leaf. Of course, these leaves are inside my manifold, and they have a complicated dynamics, but in the universal cover, they are really round disks. And when I take some element eta inside a section here, and I take a sufficiently small epsilon, this curve, this disk will become a quasi-disk. This is the image of a disk under a quasi-conformal transformation of the whole sphere. But I will still have that, because everything here is holomorphic. After doing this, I have a foliation. I have my manifold. It hasn't changed. My foliation has not changed. But what I have changed is the projective structure along each leaf. Okay? And this happens in a consistent way. The projective structure still varies holomorphically. Okay? So that's that. Okay. So one of our first results is to establish that. So I had my round disk. I added a small quadratic differential. I deformed it. Every one of the leaves, the geometry of every one of the leaves gets transformed into a quasi-disk. This quasi-disk it's a quasi-disk. It is bounded by a Jordan curve inside P1, and it has a complement. Okay? And our first result is that we can glue together all these complements and produce, by gluing them in the same way the leaves of fx on x over gamma are arranged, we can glue them and we can produce a compact complex manifold. Okay? If I do not add the quadratic differential, then, here I have my disks, and here I have the complements of these disks glued in the same way, essentially. And what I'm telling you is that we can do this even after having deformed our disks by adding these small quadratic differentials, by transforming them into quasi-disks. We can glue together the complementing disks and produce compact complex manifolds. Okay? So this is the reflection construction from this data. So my manifold, my foliation, my original projective structure, and a quadratic differential. We can produce another foliated projective structure. I will produce a new manifold. Let me call it Y eta. So we will produce a new manifold, another foliation, and another projective structure along the leaves. Okay, so I am not telling you how this is done, but you can glue this together. Another foliated projective structure.
Deforming omegas over gamma.
Say what?
Is this one deforming omega over gamma?
Yes, so okay, so okay, so I am not telling you how I'm doing this. It's just gluing the complementary disks to my quasi-disks in the same way. Okay. Come here.
Well, are you saying that you have a map from A0 KF2 to A1 of EY0?
That's the theorem. Let me tell you. Let me state it. So, and the theorem is this. So, we have some domain U, neighborhood of the origin. So for quadratic differential sufficiently small. And I will tell later, I will explain this statement now. So I can forget about the foliation and the projective structure and just keep my compact complex manifold. This will give me a family of compact complex manifold parameterized by a neighborhood of the origin here. Okay? And this family is effectively parameterized. So I will say what effectively parameterized is. It means that, it means that in the theory of Codiron-Spencer, you are using all the parameters to produce deformations. So this will give us true deformations of this manifold. So, this manifold was constructed as a quotient, so it produces a deformation of this manifold. Okay, so this manifold is produced as quotient of some domain, and there are some of a flag domain, and there are some results by Dumas and Sanders that tell you that under certain conditions, when you have an anossov representation acting on a flag manifold, producing a complex manifold, it tells you that you can produce all the deformations of your compact complex manifold just by deforming the group. This is not the case here because the group is inside PU21, which is inside PGL3C. And as a subgroup of PGL3C, this is a rigid group by Weyl's rigidity theorem. You cannot deform this group. So these are so even if you know this manifold is constructed as a quotient, you cannot use this information to deform it. You cannot deform the group. You cannot deform the geometry. So this produces an explicit way to give deformations here. Okay? So let me comment on this statement. So this is joint work with Bertrand de Rouen, who's not here. So the Kodaira-Spencer theory tells you that if you have, like here, a family of manifolds, so a family of manifolds means you have a bigger manifold and a submersion such that the fibers are compact manifolds, and this is your family of manifolds. So this is a family in the sense of Kodaira-Spencer. And you have this Kodaira-Spencer map, which is in some sense the derivative of this family. That goes from the tangent, say you choose a point here in U, and it maps into this space of, so this is your central fiber. Let me put M0, MP. So it's a differential of the family at P with coefficients in the tangent sheaf of PM. So this is the derivative of the complex structures of the family. And so if you have your family of, you can also think of your family of complex structures as given all these complex structures by the same charts, but whose gluings depend on the parameter in T. So if you consider this notion, then when you have two overlapping charts, and you have one parameter, one deformation direction within U, what you will get is, in the overlap of these two charts, you will have some movement, and this movement will produce a vector field on the intersection of your domains. This depends on the charts, but this cohomology group does not depend on these charts and is well defined. Okay? And what we think we have is something that goes as follows. So this will be, so what happens is this H1 can be, in fact, I have here the image. So over some extra arithmeticity hypothesis, so we can use a theorem due to Carayol, this is the picture that emerges. So I have here my H1 of omega over gamma. I have here the image of the quadratic differentials of x over gamma here. The other factor will be the space of quadratic differentials of the third domain, which I did not tell you, that it has another foliation, the foliation where I fix a point and I make the line move. And these appear in, this is a direct sum. So this is the linear drawing. So this space, the H1, where the derivatives of the complex structure take place, is the direct sum of the images of these two spaces. One comes from this theorem, and the other comes from an equivalent formulation for the third domain. And we would like to know if this is the infinitesimal drawing, and we would love to know if this is the true drawing, if this gives the space of deformations. So along the first deformation, we are preserving the transversely foliated compact manifold, but we are deforming along one foliation. And at the other one, we are deforming the other foliation. We do not know if there are other foliations, other deformations that can of this manifold, of this non-classical flat domain, as people call it. We do not know if there are other ones or if these describes all the deformations. So it does infinitesimally, at least, or it appears to do so. And I think that this is a good place to stop. Thank you very much.
Thank you, Adolfo, for the nice talk.